and welcome to another WJEC A level physics question. This time is question 7 from June 2009's PH5 paper, and it's on particle accelerators and magnetic fields, which are currently found in Unit 4. So we've got a diagram of a synchrotron, and we've got to explain how a proton would be accelerated within a synchrotron while maintaining a path of constant radius. Well, first of all, the proton is accelerated by an electric field. In the gaps. So when we're looking at the diagram on the right, these regions here are known as drift tubes, and the gaps in between them, that's where the protons will be accelerated, because there'll be a potential difference between one drift tube and the next drift tube. One tube will be positive, one will be negative, and the proton will be attracted towards that negative tube. Next, we've got to explain how the proton goes around in a circle. So what we're going to say here is that the magnetic field produces a centripetal force. Now what's going to happen is, as the proton is going round and round the synchrotron, it's going to be speeding up every time it passes through a gap, and because of that we need to increase the magnetic field as the proton accelerates. I'll just call it a B field to save a little bit of writing. But also at the same time we have to increase the frequency of the AC supply that we see here, so that the relative polarity of the drift tubes is correct every time the electron leaves the tube. So let's just continue that by saying, and the frequency of the supply is increased. Okay, next, on the above diagram we've got to indicate with crosses the 4 regions where the speed of the proton is increased. So we've already mentioned that's these 4 gaps. And we've also got to sketch the path and direction of the accelerated protons. So I've already sketched the circular path. Now we've got to work out the direction of the protons. So the way that we're going to do this is to use Fleming's left-hand rule. So the first finger, remember, represents the direction of the magnetic field, which is out of the page or out of the paper. Your thumb represents the direction of the force. Now because the the protons are moving around in a circular path, we know that the force will be towards the center of the circle. So we're going to point the first finger of our left hands towards ourselves, point our thumb to the right, and taking the position where I have on the diagram, you should then see that your center finger for the current is pointing up the page. Now current is the direction of flow of positive charges, and protons are positive charges, so hence the protons are going to be going around this circle in a clockwise direction. Next, the radius of the proton path is 4.6 meters, and when the frequency of the AC supply is 1.9 megahertz, we've got to calculate the speed of the protons. So here we can use V equals 2 pi r over t, or if you prefer, V equals 2 pi rf. I think this way is slightly easier with the t bit. So what we've got to think about is 2 pi r is the circumference of one revolution of our protons as it goes around the synchrotron. We've got to think about the time that it takes for the protons to do that. Well, the period for the AC is 1 over 1.9 megahertz. If we do that on a calculator, we get about 5.3 times 10 to the minus 7 seconds. But what we've got to remember is that the AC supply has to switch over twice during one cycle. So the AC supply is going to switch over every time that a proton enters a new gap, and it enters the new gap 4 times in one cycle. So we got a half cycle when we pass through the first gap, then another half cycle for the second gap, and so forth. So the time that it's going to take our proton, to complete this orbit, would actually be double that time of 5.3 times 10 to the minus 7 seconds. So let's calculate V by putting in 2 pi, radius of 4.6 meters, and 2 lots of the 5.3 times 10 to the minus 7 seconds. And that will give us an answer of 2.75 times 10 to the 7 meters per second. Next, we're going to calculate the magnetic flux density. Well, what we're going to do here is we're going to start with the magnetic force, BeV. Remember that protons have the same charge as electrons, is equal to the centripetal force, mv squared over r. We can cancel one of the v's, and a simple bit of rearrangement shows that we end up with mv over e times r. The mass of the proton is not in the data books anymore, but it used to be, and it's 1.67 times 10 to the minus 27 kilograms, just slightly more than 1 U is one way of remembering that. Nowadays they tell you in the question what the mass was. The speed we've just worked out is 2.75 times 10 to the 7 meters per second. The charge of the proton, 1.6 times 10 to the minus 19 coulombs, and the radius of 4.6 meters. And putting those into the calculator, we end up with B being 0.062 Teslas. Next, the question talks about a Hall probe being used to measure the B field inside a different synchrotron. And we're given that there are 5 times 10 to the 22 free electrons per meter cubed in the Hall probe, and their mean drift velocity is 7.8 times 10 to the minus 3 meters per second. We're going to calculate the current flowing in the Hall probe, and we can use the AS formula, I equals NAVE. So we've got 5 times 10 to the 22 times the area. Now the area is the area through which the electrons are flowing, so it's an area of 2 millimeters by 0.4 millimeters. And we must remember to turn the millimeters into meters. V is 7.8 times 10 to the minus 3, and the electron charge 1.6 times 10 to the minus 19. Didn't really leave myself enough room to put that in. Put those into the calculator and we get a current of basically 50 microamps, 49.92. To calculate the Hall voltage, we can use this equation. VH is BVD, and that's not given to you in the data books, but you are actually allowed to use it if you remember it. If you don't remember it, then we can explain this in terms of the fact that when the Hall PD is set up, the electric and magnetic fields balance each other out. So let's do a very quick magnetic excuse me, a very quick derivation. The electric and magnetic forces balance each other out. The electrons go straight through the middle of the Hall probe there. Formula for an electric force is E times Q, or in this case E times E, and the formula for a magnetic force is BeV. And you'll see that the E's will cancel. But also the formula for an electric field between two charged plates, for example, is V over D, where V is the Hall voltage. So you should be able to see fairly clearly that VH is BVD, so it's not too difficult, the derivation. So let's put in the figures. The magnetic field strength was 0.3 Tesla. The velocity of these electrons, 7.8 times 10 to the minus 3. And the D here is going to be the distance between the two plates. So what's going to happen here is one of these plates is going to become positive, one is negative. I'm calling them plates, it's just the top and bottom of the Hall probe. And the D that we're going to use here is the distance between them of 2 millimeters. Putting those into a calculator, we get 4.68 microvolts. 4.68 times 10 to the minus 6 volts. Thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.